Great. So, hey everyone, my name's Freddie here from Team Unifrog, and I can see lots of you joining us. So we will wait just a moment for a few more of you to come onto the webinar. But thanks for those of you that have joined promptly. Great to see over 80 of you joining. So we're really excited for this one. We've got about 45 minutes. Now, pretty much 100 of you having joined us. So thank you so much. We will get started straight away. I'm joined by Professor Simon Vaughan from the University of Leicester and Avi as well, a current student at Leicester. And so Simon's going to be delivering his talk around understanding black holes. And then about 5 p.m., we're going to be doing a Q&A as well. So please do use that Q&A function that you'll see in your browser to fire your questions throughout the session, and we'll make sure that we get those answered. But yeah, only 45 minutes. So without further ado, I'm going to hand over to you, Simon, to get us started.
Thank you very much. Hi, everyone. I'm Simon Vaughan. I'm a professor here at the University of Leicester in the School of Physics and Astronomy. Today, I'm going to be talking to you about black holes. I can guarantee you've all heard of black holes. You've probably read or maybe seen on TV or in the movies something about them. You may not know too much about how astrophysicists might find real black holes and study them. That's what we're going to talk about today. And along the way, I'm going to tell you about how you might see ideas from physics you studied at school and be able to employ those in the study of black holes, and then the kind of physics you might learn about if you go on to university to study physics. And towards the end, I'll tell you how that connects with our courses at Leicester. Okay, so here we go. This is me. This is a nice picture of the view from the other side of our physics building, looking over Victoria Park. It doesn't look like that today. It's rather grayer today. This is clearly a sunny day. Right. I'm going to divide this into 3 parts. The first part is an observational story. This is how observational astronomers might think about black holes, try to find them and study them. Then we'll go on to part 2, which is the more theoretical side. So we'll bring in understanding of the physics and how that builds into a theory for how black holes might behave, how that links to the observations. These are probably going to sound quite different from the stories about black holes you might see on a television program or in a book by Brian Greene or Stephen Hawking or one of those people. They are very mathematical. They try to put into words the complicated mathematics behind this, what goes on in the very core of a black hole, etc. I'm not going to go into that kind of detail. I'm going to tell you about how we real astronomers find real black holes out there, not necessarily the mathematics behind them. Right, so here we go. Hopefully this makes sense. I'm going to start my story a long time ago, well, probably a long time ago for all you people anyway, in 1975. This is a patch of sky, fairly boring patch of sky, seen in the visible band, the kind of light your eyes are sensitive to, but with a pretty good telescope. And you can see a fairly normal star field here, except we've marked, if I can get my cursor to go, here we go, we've marked with a little L here, a particular star just there, which looks kind of boring at the moment. You would not think anything interesting is going on there. Except in 1975, we at the University of Leicester, this is before my time, 1975, but at the University of Leicester, we were making X-ray cameras to go into space. This is an example of a space telescope. It doesn't look very impressive. It looks like a dustbin in space, but this is the UK's first astronomy space mission. And these blocks on the front are part of an X-ray camera. It works a bit like a Geiger counter or something like that. You scan it across the sky, and when it's pointing in a certain direction where there's lots of X-rays, it records a strong signal. You move away, you rotate away, it's a spinning satellite, you rotate away where there's no X-rays coming from space, and the signal goes down. And that's what it was doing. It was spinning around in space, trying to find sources of X-rays from the edge of the solar system or the galaxy or beyond the galaxy. We really didn't know at the time. What are X-rays? Well, they're a kind of electromagnetic radiation. They're a bit like light, infrared light, visible light that you see with your eyes, ultraviolet light, except they're higher energy. The higher energy is important. X-rays tend to be produced naturally only by very hot or very energetic processes. So in 1974, this mission got launched. It's a joint UK-American mission, and it was scanning the sky through 1974 up until about 1980. Why was it on a satellite? Why not do this from the ground? Big telescopes from the ground, right? Well, usually yes. Depends on the kind of light you're looking at. Our atmosphere absorbs X-rays. That is a problem if you want to do X-ray astronomy. It's a great idea if you want to be alive because X-rays are dangerous. So the atmosphere screens out a lot of harsh radiation coming from space, coming from the sun, etc. But when you want to go and observe that kind of radiation, you need your telescope or your instrument to be above most of the atmosphere. And we can fly X-ray cameras on very high altitude balloons, launch them on rockets for up to maybe 300 kilometers, and then they stay there for 5 minutes and come back down. But really, we want to get one on a satellite so that it's up there for years and taking continuous and long observations. That's why X-ray astronomy is done from space, to avoid the atmosphere entirely. That also means our cameras tend to be a lot smaller than an optical telescope. On the ground, we now have 10-meter wide telescopes, and the European Observatory is building a 30-meter wide telescope. That's enormous. There is no chance of launching anything like that into space, even with Elon Musk's biggest rocket. Instead, we tend to deal with telescopes and instruments that might be half a meter wide. But for X-ray astronomy, that is big. What happened? Well, in August 1975, this satellite was scanning the sky and there was a sudden increase in X-rays from a particular direction. Here is a graph taken from a paper that was published from Leicester in 1975. And it's a bit of a rubbish plot. I would hope that you could, if you join us as an undergrad, we'll show you how to make much better plots than this with modern technology, but they didn't have computers the way that we do now. What's shown here is the date along the bottom, and the date is in this strange system of units. It's counting in days, but it's in modified Julian date. Don't worry about what that is. It's a particularly odd form of date system used in astronomy, but it's standard, so we use it. And then on the vertical axis, what we show is the X-ray brightness as seen from this Ariel 5 satellite, this UK Leicester built camera, on each of these days. And you can see what happens is at the beginning of this series of observations, it's very faint, very low on the graph, and it just rises and rises and rises and rises up until it's hundreds of times brighter than it was. Nobody knew there were X-rays coming from this direction before. Suddenly something appears and it just gets brighter and brighter and brighter over a couple of weeks. Now, this thing was called A0620-00. Why is it called that? Why do objects in astronomy have such peculiar names? It's called A because it was discovered by the Ariel 5 satellite. It's called 0620-00 because those are the coordinates on the sky. They're the very rough coordinates anyway, available at the time. Rough coordinates on the sky that these X-rays were seen from. There's an awful lot of objects in astronomy. We can't give them all nice names like George and Alice. So instead, we tend to call them by after the satellite or instrument that discovered them, and then their coordinates. Then we find out what they really are afterwards. This thing, a 0620-00, we tracked it for years and decades. What we saw is that it peaked in 1975. It stayed bright for 100 or so days, and it slowly faded after that. When it was bright, it was very bright. It was the brightest thing in the X-ray sky. At the time, we didn't know of many things that were bright in the X-ray sky, but we knew about neutron stars. They could be very bright. We knew about supernovae. They could be very bright. The sun is a very powerful source of X-rays. This thing was something new that we'd not seen before. So what could it be? That's when we need scientific detective work. We need to understand what we saw in the X-rays. We need to look at it in every way that we can to figure out what this was, what produced such powerful X-rays from this one direction, where there's just this odd-looking star, perfectly normal-looking star, in fact. Nothing special about it. Right, so the game is afoot. We go back to our star map. The X-rays were from roughly this direction. Radio maps, radio telescopes looked and they saw something bright, getting brighter, and they were able to pinpoint the position a bit better until we find ourselves looking at this star here. But that just looks like a normal star. If you know anything about astronomy, you might know about magnitudes. That's how we typically measure the brightness of an object in the sky. This is 12th magnitude. That's way fainter than you can see with your eyes, even on a very clear night. But there's thousands and thousands of stars that brightness. Nothing terribly special about that. It looked a bit blue, but again, there's plenty of blue stars. People stared at this thing with a telescope, a big enough telescope that you could split the light into its spectrum from long wavelength to short wavelength. The reason for doing that is because there's a lot of information in the spectrum of a star about how hot it is, what metals, what the composition of its atmosphere is, and from that you can tell the type of star. That then leads you to the mass of the star and how big it is. So the spectrum of this star, in the direction of A 0620-00, is that of a K star. It looks like this one here. These are different kinds of stars, from hot big stars to cool dwarf stars. And this one is a K star, which is kind of a cool, small star, a bit smaller than the sun, a bit cooler than the sun. Really nothing very exciting. Why on earth is that making lots of X-rays? In case you're wondering what the naming system is, O, B, A, F, G, K, M, this is one of those historical quirks of astronomy. We have an awful lot of very silly naming systems and classification systems, and to some extent, you just have to get used to it. It's not made to be complicated. There was a reason at the time, but now that we've learned a lot more, the original reason for the naming system doesn't make any sense whatsoever, but it's too late to change it now. So K-star is not going to produce a very bright source of X-rays. It's not going to outshine everything else in the sky. So what could it be? More detailed detective work on this star, it's not a car, it's a star, showed that it seemed to be moving. If you look in real detail at the spectrum, you can see these line features. It's a bit like reading a barcode, and the exact positions tell you which elements are in the atmosphere of the star. They were moving slightly. They were moving slightly long wavelength and then short wavelength and then back again. Very small movement, but it was there and it was periodic. Now that's exactly what you expect if the star is moving. If the star is moving towards you and away from you, that will produce a Doppler shift. That will shift the frequency of the light or the wavelength of the light, depending on which way around you think about it. And that reveals the motion of the star. So this star, normal star, moving forwards and backwards, and it was doing this every 7.7 hours. The velocity of this motion was about 460 kilometers a second. That is really fast by Earth standards, obviously. Not terribly fast by astronomical standards. But what that means is that almost certainly this star is one of a binary. It's orbiting something. So there's a something and this K star, and they're going around each other. And when we see this Doppler shift, that is the motion of the orbit as it's coming towards us and away from us as it goes round on its orbit, around something else. What is the something else? That is the question. Well, we know about orbits. We have Kepler's laws. You may have studied those at school already. And we know Newton's law of gravity. And we also know about circular motion. We can put all that together into a relatively simple equation to understand what the mass of the unseen companion is. What is partnering this K star? we know the period of the orbit, and we know the mass of a K-star pretty well. We know the velocity of the orbit as well. That's enough information to work out what could be the mass of the unseen companion, the thing that this star is orbiting around. Actually, they're both going around their common center of mass, but that's a detail we don't need to get into here. Put the measurements in, and we get a mass of 3 solar masses. The companion is at least 3 times the mass of our sun. The K star is less than the mass of our sun. So the unseen companion is the bigger of the pair. Now, the reason I say the mass is a limit is that we don't know the angle of the orbit. The orbit could be going around nearly face on to us, or it could be nearly edge on to us. Now, that changes the perspective with which we see the motion. And because we don't know that inclination, we don't know how the angle of the orbit lies along our direction, we don't know that yet. We can't say exactly what the mass is, but we can say it must be bigger than 3 solar masses, or you couldn't produce the velocities that we see. And we know there's something that doesn't show up in visible light, near bound, gravitationally connected to this K star, and it's at least 3 solar masses. What could it be? Could it be a normal star? Well, it could be. There are 3 solar mass normal stars out there, but they don't produce lots of X-rays like this thing. Could it be a white dwarf? That's a kind of hot, dense nuclear waste of a star that's exploded in a planetary nebula, rather like our sun. Well, potentially they can produce X-rays, but the most massive white dwarf possible is about 1.4 times the mass of our sun. This thing is at least twice that mass. Okay, what else could it be? Could it be a neutron star? A neutron star is beyond the density of a white dwarf, considerably beyond the density of a white dwarf. It's almost like another phase of matter when you go to very high density. As far as we know, the maximum mass for a neutron star before it collapses under its own gravity, it's about 2, maybe 2 and a bit solar masses. So the limit on a white dwarf, this 1.4 solar masses, that was worked out by Chandrasekhar in the 1930s. Brilliant bit of quantum physics applied there. And the maximum mass of a neutron star was worked out by Oppenheimer and Snyder. Oppenheimer's was the subject of a very recent movie you might have seen. Before he did all that stuff that's in the movie, he worked on neutron stars. It can't be any of these, because the mass we have is at least as big or bigger than all of those. The only thing we have left in our list of possibilities is a black hole. A black hole can have a mass of 3 solar masses. It can be invisible in the optical, in the visible light, which is the reason we didn't see it next to the K-star, and it can be a powerful source of X-rays. Well, how is it a powerful source of X-rays? It can be a powerful source because it's in a binary like this. It's interacting. If I switch on my little laser beam, black hole is in here. The dwarf star is here. They are gravitationally bound to each other and orbiting. But something has happened. The dwarf star is donating matter towards the black hole. That produces an accretion disk. That gets extremely hot, and that produces X-rays. The X-rays, the radiation, are not coming from the black hole itself. They're coming from the material spinning very close to the black hole on its way down the hole. Before it gets there, before it gets to the important parts of the black hole we'll talk about in a minute. And the reason we spotted a 0620-00 is because it went to an outburst. This accretion disk switched on to a hot phase, produced a huge amount of X-rays, and as the black hole swallowed most of the material in the disk, it then ran out of material to feed on and went quiet again. And it's been quiet since 1975, that one. But we now know many more examples of these. This was one of the first discovered and one of the first to be identified as a black hole. But since then, we found about 30 of these in our galaxy, and then more of them in other galaxies. And roughly once a year, or maybe once every 2 years, we discover a new one. Completely unknown X-ray binary. It suddenly goes into outburst, gets super bright, and one of our X-ray satellites spots it. Right, so in the optical, we saw the K star, normal star, temperature of a few thousand Kelvin. glows brightly in the red, blue, green kind of bands. In the X-rays, what we were seeing is the accretion disk. In fact, just an inner region of the accretion disk in here. The black hole is a teeny tiny dot in the middle. Its strong gravity is pulling on all this stuff swirling around it, and it brings it to a temperature of maybe 1,000,000 Kelvin. Way, way, way hotter than the star, way hotter than any kind of star, but hot enough to glow in X-rays. Right, so finding black holes, you'd think it's a challenge. They're black. Space is black. It's hard to see. Black foreground on a black background. But because of the strong gravity, when a black hole is not by itself, but in a binary, and they're close enough to interact, it can be fed by this star. The star is a donor towards the black hole. That can form a powerful accretion disk, lots of radiation from that. But the easiest way to see them is using X-rays because they stand out. There aren't many things that are 1,000,000 degrees or hotter, but these are. To see them in X-rays, we need space missions, and we need a certain amount of patience because there aren't that many of them. Careful follow-up with lots of telescopes is needed to identify the details, figure out the velocities, exactly where they are, and understand, are they black holes, are they neutron stars, or are they white dwarfs? Because there's all of those out there. Right, here's the theoretical side. This is maybe a bit more like the story of black holes you've seen before. Here's a modern idea of a X-ray binary system. And we've talked about most of this. The key idea is that the donor star passes material at a steady rate, a low but steady rate towards the black hole, but it doesn't just fall down doesn't go down the throat of the black hole. Black hole is not like my Labrador at home that just eats anything that goes near it. In fact, this material goes into orbit around the black hole. Just as a planet goes into orbit around the sun, just as a moon orbits the Earth, satellites orbit the Earth, it goes into orbit. A black hole isn't this cookie monster that eats everything. It only eats everything that gets too close to the event horizon. This material goes into orbit. That's fine. It seems stable there, except the constant supply of more material from the donor star. And that means the orbits fill up. The gas starts rubbing against itself, and it spreads out. And then more material comes on. It goes into orbit again, but then it crashes into itself and it spreads out further until it fills something called an accretion disk. And there is a slow but steady drift through this disk as mass slowly works its way down towards the black hole, slowly pulled down by gravity, but it's going around and around and around millions of times for each step inwards. Now that's how it works most of the time. But then when the pressure in the disk gets too high, it gets hot and it swaps from being fairly neutral gas to being a plasma. And you might have studied, or at least know what a plasma is. A plasma is an hot ionized gas. Now, plasmas conduct electricity much better than neutral gases do, and they can generate magnetic fields, and then all sorts of complicated physics happens, and that speeds up the flow of material. It suddenly starts falling towards a black hole much faster. That's why this A0620 -00 suddenly went into outburst. The accretion disk was full, it switched into a plasma, and suddenly a lot of material fell towards the black hole. Right. Here is a description of the gravitational field around two masses. This is the donor star. This is the black hole. And what we've drawn here is the contours of the gravitational potential. And again, that might be something you've studied already at school. Don't worry if not, but if you go on to physics at university, you definitely will study this, probably in year one, certainly year one if you come here. Right, and what we've done here is we've drawn contours of equal gravitational potential. And the black hole, it looks bigger, but it's not. The black hole is just a dot in the middle, but it's got more mass, so it's got a bigger gravitational field. The dwarf star is here, the K dwarf star is here. And if the K dwarf star fills its little lobe here of equal potential, if a single atom just spills outside of that, that means it's pulled more towards the black hole than it is towards its own center. Any material that gets to this crossing point, called the L1 point, it's not halfway between the black hole and the K star. It's not halfway between the two. It's between the two where the force of gravity pulling one way and the other way balance exactly. If you cross that point, then a single atom crossing that point is then pulled more towards the black hole than it is towards its original star. So any material touching that point starts to flow towards the black hole. And it flows in, it goes around. I'm sorry, this is a bit of a rubbish picture. I couldn't find a better one. It goes around the black hole, crashes into itself, and spreads out into a disk. Right, what happens next? What happens when you get closer to the black hole? Well, black holes are strange creatures. They're either very complicated or very simple, depending on how you think about it. They're a prediction of Einstein's theory of gravity, general relativity, and the theory of black holes shows that they are, in some ways, they are very simple objects. They're described only by mass and spin and electric charge. They've got no other properties at all, at least in the standard theory. So, as a human, you have a certain weight, a height, an age, you've got eye color, you've got, all sorts of properties, memories, and all the rest of it. Black holes have no such thing. They are described by 3 numbers, and that's it. Which is a very curious thing. Even most elementary particles have more features than that. But black holes really are very simple in that sense. And in fact, real astrophysical black holes, they don't even have an electric charge. Because if you try to charge up a black hole and make it very positive, it will then pull in a load of negative charges from the surrounding environment and neutralize itself. Opposite charges attract, so that will neutralize. Real black holes, all you need to know is the mass and the spin, and everything there is to know about that black hole. But the defining feature of them, the thing that makes them different from a planet, a star, a white dwarf, or a neutron star, is the event horizon. That is the boundary of the black hole where the escape velocity reaches the speed of light, which means that it doesn't matter how fast you move, once you've crossed that horizon, you can't get back out of the black hole. That's why they have the name that they do. They're black, light can't escape. Black seems like a natural choice to describe them. But if they're black, shouldn't they be very hard to see? And yes, of course they should, if they are alone. Black hole in isolation would be extremely hard to see. But a black hole being fed material from an accretion disk can be very easily seen, because the accretion disk is a huge source of light. The black hole happens to be a black dot in the middle, but around it is very well illuminated. How big is one of these? Well, very small, in fact. From the equations of relativity, we can see that the event horizon lies at about 1.5 kilometers distance from the center for every solar mass inside the black hole. The black hole in the object I talked about, A0620, is maybe about 8 solar masses. We think now it's at least 3, maybe 8. So the event horizon is about 4.5 to maybe 15 kilometers out from the center. That's not very big. I mean, compared to a house or a car or a person, that's huge. But compared to a star, that's not big at all. That's smaller than a city. And yet this thing has the mass of 3 suns inside it, at least. That has a devastating gravitational field if you get too close. How do we see? How do we measure this field? Lots of different ways. One of them is Doppler shift. The material around the black hole, it's going at nearly half the speed of light when it gets close to the black hole as it orbits. That produces enormous Doppler shifts that we can measure. There's also a gravitational redshift. The pull of the black hole actually distorts the colors of the light emerging. Those are things we can measure in the spectrum. But what we can't measure is the event horizon itself. Anything that crosses that is dark, we don't see it. But we can see any material that gets close up to maybe 2 or 3 times from the event horizon. Beyond that is very hard to see. What else happens near a black hole? Well, some very strange effects. One of the strangest is light bending. This is when light that you would think would go in straight lines doesn't. It gets pulled around by the gravity of the black hole. And in fact, some of the light that gets emitted by the accretion disk, it goes up, gets bent around by the black hole and down again. So just tracking the flow of energy of this thing turns out to be quite hard. But this also has uses. It means we can see time delays. Sometimes part of the accretion disk flickers, and we see it flicker, and then we might see an echo of the flicker because the radiation has gone around the black hole or bounced off the accretion disk. And that time separation between those echoes allows us to map out parts of the accretion disk immediately around the black hole. The other thing that happens is tidal forces. You may have read about spaghettification and how everything gets shredded on its way into a black hole. That would be true for a solid object the size of you or me, but not for an atom. An atom's not going to get split on its way down the black hole, but the gas is going to get torn apart. Here's an illustration of tidal forces. You may have done them in your school physics as well, where here's 4 objects, A, B, C, and D. You can imagine A as your head, B as your feet, C as your one arm, D is your other arm. And as you point towards the black hole, because your feet are closer, they're pulled more, the gravity is stronger. Your head is further away, it's pulled less. So your head and your feet are pulled apart. That's a tidal force. And because your arms are out at an angle, each of them is pulled towards a black hole. That means they're pulled towards each other to some extent. So material moving directly towards a black hole will be stretched in one direction and squeezed in another direction. That's the tidal forces. They're very powerful and they will shred nearly everything. I'll come back to that right at the end, but not enough to split atoms. So we still have whole atoms orbiting near the black hole. Right, where are we now? We know about 30 black hole X-ray binaries. We know maybe 100, more than that, neutron star X-ray binaries. They're more common, and we discover about 1 more black hole a year. We can track them through these outbursts. One discovery from a couple of decades ago that was rather unexpected at the time is that sometimes they produce jets. They fire out material from either side, and we can see that moving, even though this thing is a few kilometers across and it's at maybe 1,000 light years. You can't see that, it's just a speck. But they fire out these blobs of radio emitting material that move fast enough you can see them across the sky. You can see it expand over the weeks. While we're waiting for these, we figure out how to observe them better and build computer models for them. Right. Now, I mentioned a lot of physics there. There's gravity. You've got to understand Newtonian gravity, that's the kind you learn at school, and Einstein's gravity, which you can learn towards the end of a physics degree, for example. There's some quantum physics there. How big can a white dwarf be? Well, that depends on quantum physics. What kind of emission do we get from the surface of an accretion disk? That's quantum physics. You need to know about Doppler shifts because this gas is moving really fast and it gets blue shifted and red shifted, and you can use that to understand the orbits. You need to understand a bit about how fluids flow because the accretion disk really is flowing fluid in a disk pulled by gravity. You need to know about heat. How does the accretion disk radiate? And a bit about particle physics. Those jets are fast-moving particles, so we need to have streams of photons and electrons in there. And then you also need to know about magnetism, but I'm not going to mention that because that's probably the hardest thing in the list. On a physics degree, you can learn about all of those. Right, what do we do at Leicester? We do lots of black hole research. We study gamma ray bursts. Just down the hall from me, there's an office that study gamma ray bursts. They could be forming black holes. We follow up on gravitational wave signals. So in 2017, I think it was, the Gravitational Wave Observatory, its first discovery, won the Nobel Prize. We don't work on the gravitational wave detectors. We work on satellites that then track down where the gravitational waves came from. We study X-ray binaries. That's something that I work on. We study active galaxies. Those are supermassive brothers of X-ray binaries. They might have 1 million to 1 billion solar masses in their black holes. And this is a new feature. We study tidal disruption of stars. So if a star, a normal star, wandered into the center of a galaxy where there's a supermassive black hole, the tidal forces can pull it apart. The picture there is an image from the cover of this month's issue of Nature Astronomy. And it's based on a story that one of my colleagues, Phil, just down the hall from me, published this month about the discovery of a tidal disruption event. Right, so what do we do at Leicester? If you were to come to Leicester and learn about all this, you can. We have various flavors of physics degrees. We do physics, physics with astrophysics, or physics with space science, and there is overlap between all of those. We do a 3-year BSc, bachelor's degree, a 4-year master's MPhil degree. There's also a foundation year. You can do it with a year abroad or a year in industry. We have accredited degrees. They're accredited by the Institute of Physics, that's the IOP. And our program, we call it research-inspired education. So the research I talked about before that started in Leicester in the 1970s and is still going very strong now, that's in a lot of the teaching that we deliver. We're very well rated by students. We're among the top in the National Student Survey when students get asked about how was your course, how interesting was it, how satisfied are you with the department? And there's a ton of astro and space projects you can get involved with. So if you're interested, ask us questions, apply to us if you're coming to university next year, or book a visit with us. Right, and that is me done. So thank you very much for listening. Avi and I are now going to hang on to try and answer any questions.
Thank you so much, Simon. Really, really good. And yeah, the questions have been absolutely flying in, which you won't have known, but the team at Leicester have been doing a great job to get as many of those answered as we could over the last half an hour. But with literally just 9 minutes left, I think we're going to have to shoot through some of these, and we got 34 in the inbox. So let's see how we get on. There's definitely, a pattern of questions asked here. But let's start with this one. How is time affected by black hole gravity? I find the concept really complex to comprehend.
Everyone does. It's really hard. One way of dealing with it is to try and understand the mathematics. Just work through the mathematics and not worry too much about understanding what's going on to time and what's going on to space. At some level, though, you want to interpret it. But the reason why, and Avi can probably testify to this, the reason why us humans, us mortal humans, come unstuck with anything to do with relativity is we can't help but think of space as one thing and time as another. You have to throw that idea out. There is just one thing called space-time, and then you draw a space-time diagram and it all makes sense in the diagram. When you then try and think, okay, what does this mean with my mortal brain? You can't help but separate it into time and space, and then it never quite makes sense again. You just got to think about it in terms of space-time. Now, when you get close to a black hole, people do say things like time slows down. And that's the gravitational redshift. I mentioned that. I said that light emitted from near a black hole, it kind of gets pulled towards the red side. It gets faded and reddened. That's the same thing as saying time slows down. It's the same physical effect, because the waves that are leaving this fast from near the surface of the black hole, by the time they get to us, they've slowed right down. They've gone to longer wavelengths. It's exactly the same effect. It's just a different way of thinking about it, and probably a bit easier to think about it that way.
Fantastic. One more for you, Simon, before we perhaps move on to Avi, but I had one here. Why did it take us so long to discover black holes if there's such a massive one in the center of our galaxy?
That goes back to the issue of it's black. It's really hard to see unless it's accreting, unless it's pulling stuff in and tearing it apart and making it really hot and firing out jets. Unless it's doing that, it's really hard to see. The center of our galaxy has a black hole with the ridiculous name of Sagittarius A star. It's in the constellation of Sagittarius. It is a radio source. It's just a blob of radios coming from the middle. No one was quite sure what it was, although pretty good idea. It probably had to be a black hole. But that really wasn't confirmed until maybe 20-ish years ago. There was really very convincing evidence that it was a black hole. So it had to be compact, very, very small for its mass, and very massive also. The center of our galaxy is probably good for us, is not a particularly active galaxy. It's a very quiet black hole in the grand scheme of things, which makes it a bit harder to notice.
Yeah, definitely. Thanks so much, Simon. Avi, I wondered if you could sort of introduce yourself, how long you've been studying at Leicester, and we had a question for you here as well. How much have you studied black holes in detail? And it'd be really good to find out, how you've been spending your time and what you have been digging into in your studies.
Sure. So I am a physics student at University of Leicester. I finished my second year of physics and I'm on a year in industry at the moment, working at the university, and this is a year-long placement, and then I'll get back to my third year. So in terms of black holes, so my degree is general physics, but still, as Simon mentioned during his talk, that we do have quite a bit of overlaps. So I have done some astrophysics related courses during my degree, during my first and second year, which are like electives. And we've studied black holes to some extent, but obviously not in elaborate detail where general relativity and things like that get introduced more as we move on into higher years like year three and year four, where you do get a really good amount of insight, even like a qualitative insight when you're in your second year, for example, studying intermediate astrophysics. So if that answers your question.
Yeah. No, I think you've done well there because we we are short on time, but I think that was a really good overview and really keen to find out a bit more about your placement year and in addition, what type of careers, that was one of the other questions, are there available to go on to with your kind of degree, and what do you hope to do personally as well?
Yes, absolutely. So my placement is quite different from physics, but there's a lot of transferable skills to gain as part of it. So I work with the college student recruitment and marketing team, facilitating the College of Science and Engineering, one of the schools being physics. And this involves lots of different kinds of outreach activities, recruitment, strategy planning, and liaising with all academic directors and stuff. But as that is also kind of related to some sort of data analytics that you do. So really looking into data is where I was able to transfer my physics skill sets that I learned during my first years and second years to be able to really probe on and understand the data from a physics perspective and help make marketing decisions. But that's about
Wow.
my placement. In terms of the different kinds of careers you could pursue, you could be pretty much anything with a physics degree, honestly. The amount of plethora of skill sets and the versatility of things that you learn, starting from maths, physics, coding. Um, we also have modules where you learn about business startup methodologies and stuff like that. You really, really learn a diverse amount of skill sets which are transferable in pretty much any field. So you can become anywhere from a theoretical physicist all the way to an experimentalist, or even work in the finance sector, or even let's say build instruments for F1 or something like that. So there's plethora of scope.
Amazing. And is it standard to do the placement year on your general physics course, or was that, something that you pursued and looked for when you were choosing a degree?
So, well, in terms of the options that you have, you can have a sandwich here where you could either do a year in industry or study abroad.
Yeah.
And I chose to do a year in industry because I felt it is such an important opportunity for you to develop on your CV and learn professional skill sets, be able to build on different transferable skills that you might not have been able to work as part of your degree. Or you could potentially even build on doing some kind of physics research that will help with your portfolio once you move into the job sectors later on after your degree. Um, I wouldn't say it's always standard, but particularly in my year, I saw a lot of people take up year in industry and study abroad. So that was quite
Yeah, yeah.
exciting.
I've noticed actually on the Q&A, there's been a few questions about study abroad, and I
Mm.
think that's an excellent way. I think it will complement what you're already learning on your degree and just adding extra skills, isn't it, by being abroad and diving into a new culture, learning a new language, having to make friends, building that resilient side of things as well. So definitely an excellent thing to do. Um, so Avi, what would you say has been the biggest sort of challenge for you arriving at the university and doing your degree, and how have you kind of adapted?
So I feel in terms of biggest challenge, it has to be experimental physics. So I've never been quite an experimental physicist. I've always been fascinated by maths and how maths is really interconnected with physics and understanding everything from more of the equation side and maybe try and make some physical intuition. But when I was put in labs on my first year, I was pretty much stumped and I didn't know how to really cope with it. But eventually, after doing it quite a lot with different team members, working as part of a team, conducting experiments together, really thinking about how you set up that experiment and what are the physical phenomena that governs the whole experiment, trying to prove the things you already learn in your theory courses was very exciting for me. And I learned a lot of skill sets such as report writing skill sets, data analysis, and lots of coding. One of the modules Simon teaches himself is on data analysis. So that's something that has been very, very helpful in analyzing data that you obtain from experimental physics. And the professors have been really, really supportive in that regard. So that really helped me overcome this kind of gap that I've had between theoretical and experimental side.
Yeah, brilliant. Thanks so much, Avi. I did want to ask one last question just before we wrap up because we are just about out of time. But I was wondering if you had any final kind of top tips for students here today that are still wondering whether physics is kind of the right fit for them, and what kind of fed into your decision making. And yeah, what would you advise students?
Yes. So, firstly, I would say if you're curious about understanding the universe and how everything works around you, pretty much the degree for you is physics because we really explore all those kinds of things, go into tremendous detail, and we really have broad perspectives of things that we look at, as I already mentioned, while discussing career prospects. And one of the main advices that I would probably put forward to anyone is no question is a stupid question. And at Leicester, we have something called open door policy for professors. So you can pretty much go and knock on their door at any time of the week and pretty much ask them any questions, which is very, very handy. And I've done that multiple times shamelessly through my degree, which has been very, very helpful, especially before exams. But please, please do not stall your questions until your exams. Please revise well and ask the professors different questions as you go through your degree. That will be my advice.
Super. What a way to end the session. That was fantastic. Thanks so much, Simon and Avi, for delivering today. And I did just want to flag what I put there in the chat to all of the students with us today. If you do have any more questions, you've got an email address in there that you can use. And then also on Leicester's website, you can speak to current students, just like Avi, on the sort of uni buddy side of things. Otherwise, thank you everyone so much for coming. And we really hope to see you at the next one. Thanks, everyone.